Be welcome to our final presentation for Engineering Senior Design at the University of Central Florida. After extensive effort and countless hours of dedication, we have successfully developed a fully functional system that meets all of our expectations. We have overcome technical obstacles and challenging deadlines since the summer semester is significantly shorter than fall or spring. We are delighted to announce the achievement of a fully functional prototype that integrates software, a cloud live database accessible via secure website utilizing user credentials, electronic circuitry that supports hardware and interfaces it with the software, as well as a floating platform that demonstrates exceptional mechanical versatility for project mobility on any point within a lake. All components have been carefully designed and organized in a cohesive manner. As a unified team, we proudly present the completed project by Engineering Group 07 at UCF. This project is presented to Dr. Lei Wei and our distinguished professional reviewers. Group 07 is conformed by the following members from left to right in the picture: Ross Springstead, Computer Engineering; Homero Rodriguez, Electrical Engineering; Mina Jones, Computer Engineering; Said Haddadin, Electrical Engineering; and Ali Ahmed Al-Kusavi, Electrical Engineering. Our goal is to produce a low-cost but effective tool that provides reliable and significant data in real time from the lakes. This data could be used to better understand lakes' health and to predict unwanted phenomena, for example, toxic algae blooms, hazardous bacteria colonies, mosquito larvae, and other insects, and also to analyze the biochemical composition of the lake.
You go, bro.
Let's talk about our goals. During our reflection on the goals we wish to achieve with this project during our Senior Design 1 class, we came up with the following goals. Build a project that assists in monitoring, researching, and understanding the lakes around us. The project will contain sensors that collect data regarding air and water. The data collected should be stored in a place like on a cloud and accessed for review at any given time. Collected data regarding those lakes will be valuable parameters in assisting lake studies. Have a functioning floating device that will be moved using a remote control. It will contain solar panels to use the sun to help keep it running. As of right now, all those goals were successfully achieved. Some discussions helped shape our goals. We had discussions with experts on the field, like with a biologist, Julie Bortles, who works at Orange County government, that helped us get a better idea and understanding of what is present to them, what their needs are, and what could be something that should be improved with their current technology. One of the biggest takeaways was that with their current technology, they do not do as many readings as wanted because of how much it would cost them. In other words, it was a budget issue. With that in mind, we thought about how we could bring something that helps the mentioned issue, and we added another goal, which is creating a low-cost project that would provide multiple readings to help the need of experts in that field, like discussed with the biologist. All the previous mentioned goals remain valid even after the discussions we had. As of right now, all those goals were successfully achieved. We had three main objectives we defined. The project needs to be completed in the allowed time frame, meaning the 150 pages document had to be completed during the spring 2023 semester, and the project has to be built and done during the summer 2023 semester. Another objective is that it has to be fully functional, meaning all described features have to be implemented and working during the summer 2023 semester. The last objective is that the material cost should not exceed $1,000. As our goal was to provide a low-cost solution, keeping a budget of $1,000 is reasonable. When it comes to the material cost, it will be equally divided among team members since the project is not sponsored by anyone. As of right now, those objectives were successfully achieved.
Engineering specification. In this project, we have successfully completed the testing phase, bringing us closer to achieving our engineering specifications. This slide highlights three key engineering specifications and the remarkable progress we have made in meeting them. Through careful design and exact testing, our floating lab system now effectively measures the water pH and gathers data from various sensors at the desired frequency of every 2 minutes. This ensures comprehensive and timely data collection for accurate analysis. With a robust communication framework in place, our floating lab system successfully transmits the collected reading to the cloud at the designated interval of every 2 minutes. This enables real-time access to the data, facilitating immediate analysis and informed decision making. Our floating lab system boasts an impressive response time of less than 2 seconds when operated with a remote controller. This ensures smooth and precise maneuverability, allowing researchers to navigate the system with ease and efficiency.
Let's now talk about our hardware block diagram. As you can see, our project has a lot of moving parts. Starting at the top right of our diagram, we place solar panels on top of our waterproof container to achieve maximum solar energy. The solar panel is connected to our power supply to provide power to our lab toolkit and recharge our rechargeable batteries. Our power supply is connected to our PCB, ESP826, and our sensors. Since our project consists of water and electronics, we need to make sure that everything is securely waterproof. This is important because we have wires being exposed from the waterproof container for our sensors. And to do this, we use silicone to secure the extremities. Next, we have attached an RC boat to enable maneuverability in the water and to allow retrieval and deployment in the central parts of ponds. Our bug collection device consists of 2 nets and the boat itself. And lastly, our sensors are connected directly to our PCB, which then sends the data as serialized JSON to the ESP8266, which takes the data and sends it to the MongoDB database.
Moving on to the hardware comparison and selection of our project brain. Multiple different technologies can exist and be used as the brain of our project. For example, there are development boards like TI or Arduino that widely exist on the market. Some advantages are that they are already fully functional at purchase time. They have libraries available to them, and they allow fast prototyping. A disadvantage is that they can have limited process and power. Another technology is designing PCBs. An advantage is that it allows flexibility because of the custom design we do. A disadvantage is that it could take a while to have a fully functional design product, since the product might go through multiple iterations before getting the wanted result or a result that works. Let's explore the chosen technology for the project brain during Senior Design 1, which was the Arduino development board. In Senior Design 1, we did not know that development boards would not be allowed as the project brain, so we chose the Arduino board after comparing technologies. We had chosen the Arduino Uno Wi-Fi Ref 2 because of its Wi-Fi and Bluetooth capabilities, the availability of libraries with it, and the ease of use, which all made it stand out compared to the other boards that did not have features like Wi-Fi built in them. During Senior Design 2, we learned that development boards weren't allowed, so instead, we had to go the PCB way instead of using a development board.
A significant PCB design was done by hand using ruler and pencil. Then, it was transferred to Fusion 360 software to generate the Gerber files and the bill of materials. At least temperature sensor, pH sensor, air quality sensor, and the ESP-MCU will be integrated into the PCB or directly interface to the system through communication protocols such as I2C or UART. The PCB brain is at Mega 328 MCU, which is managing everything else, and it is also the master for I2C. The biggest challenge we have faced in the project is the time constraint in between the cycles of fabrication for PCB, because the summer term is very short and every cycle takes at least a week and a half. Considering the time constraints imposed by the shorter duration of the summer term, we employed a PCB Fast Development Methodology. This approach involved dividing the hardware team into two different units, each working on the same objective but in a parallel way. By adopting this strategy, we increase the probability of success by enabling two PCB iterations per development cycle instead of one. The flow diagram provided below illustrates this process. Following the completion of the second cycle, the circuit design that exhibited superior performance was selected and incorporated into a soldered board. This board is currently operating at full capacity, meeting 100% of the project's requirements. The following picture shows the actual boards that were manufactured in each cycle. Although the third cycle is scheduled to arrive around 4 days after the project's deadline, empirical results obtained from the soldered board indicates that the circuit design is able to successfully fulfill the project's requirements in the form of PCB as well. After the design phase was finished on paper, prototyping on breadboard with discrete elements was done. A mega chip was programmed with bootloader, and it was connected to the network as is shown at the right side. After functionality was successfully tested, the circuit was soldered to a permanent board which has been proved effective to manage the project multiple times. The soldered board can be observed in the picture at the left on the notebook that contains its schematic. The initial stage of circuit design conceptualizing the circuitry at a high level using block diagram format. Then, extensive research was conducted on datasheets to identify specific pins, configurations, diodes, RLC networks, and other requirement elements and connections to ensure optimal circuit performance. Upon successfully functionality testing, the circuit was transferred to a permanent board through the process of soldering. This is a more detailed view of the soldered board showing the top layer and the bottom layer. This board has demonstrated effectiveness in managing the project on multiple occasions. It is able to receive code from the laptop using Arduino IDE and to manage all sensors. The board serves as an exact replica of the PCB design to facilitate power supply, grounding, and signal communication with the specific sensors employed in this project. A customized pin socket was carefully designed and implemented. As indicated in the schematic shown, the board accommodates a connection of two I2C sensors and a one-wire communication sensor. The inclusion of an embedded 5K resistor was essential to meet the requirements of the GigFunk water temperature sensor utilized in this project. The streamlined design of the board eliminates the necessity for additional external components, simply plugging the sensors in their designated pin sockets and the system is ready for operation without any further modifications. All other pins in Atmega were connected to pin sockets just in case they could be needed, and additional pins for 5 volts, 3 volts, and ground were enabled as well, as you can see in this schematic. The system is able to collect important information in a digital form using a set of sensors, but it can also collect organic material from the lake using two lateral nets as depicted in this picture. This material can be later analyzed in the lab. The organic matter retrieved through this process may encompass various components such as algae, bacteria, plant species, and animal species including insects. This comprehensive data collection is instrumental to understand the current state of the lake and forecasting its potential future evolution.
As we know, the lab toolkit is equipped with sensors such as the pH sensor, the humidity sensor, the air temperature sensor, and the water temperature sensor. All of these sensors are connected to the microcontroller, which is the Atmega 328P on the PCB. The first PCB we designed was aimed to connect the sensors to the microcontroller so it can be programmed to receive data and send it to the ESP Wi-Fi module, which it will transmit the data through Wi-Fi to the database. In our design, we included the MCU, which is the Atmega 328P, the UART interface programmer FT232RL, decoupling capacitors, voltage regulator, and the female header pins, as shown in the schematics. All the data gathered from the sensors are being sent to the microcontroller, and the microcontroller transmits the data obtained to the Wi-Fi module, which is the ESP12E Wi-Fi module. We are using this ESP12E Wi-Fi module, which has the ESP8266 chip on the Wi-Fi board, and is capable of operating at 2.4 GHz. After the design process, we use GALC PCB manufacturing service to order our PCBs. After receiving the PCB, we started the testing phase of the PCB. As mentioned before, the PCB included its own programmer on board, which is the FT232RL. This circuit was used to communicate with the microcontroller so that we can program it using USB. The team tried to program the MCU using the USB connection from the PCB, but every time it showed an error of code uploading, so we were not able to program directly the MCU through the PCB. One of the solutions that we came up with and tried is to bypass the faulty connections of the FTDI chip placed on the PCB by using an external FTDI board that is able to act as the programmer for the microcontroller as shown in the picture. The method of using an external programmer did not work even after multiple times testing back and forth. Due to the difficulty of programming the MCU through the PCB, we tested the alternative PCB mentioned previously in the beginning, which we were successfully able to program the microcontroller and connect it to the Wi-Fi module, which resulted in sending back the data to the database for the user to further study the lake as we wanted it.
The DHT11 temperature and humidity sensor provides real-time data from the place where the lab is located at in the lake, about 15 centimeters above the water. The sensor is read by Atmega while the system is in operation and can be consulted by the user through the website by accessing the user account.
When it comes to recharging the power supply, which is batteries in our case, we will look into two technologies available. The first is to manually take out the batteries from the project and charge them using a charger, then putting them back inside when fully charged. An advantage of that technology is that it does not depend on the weather to charge the power supply. A disadvantage would be inconvenience, since the product has to be taken out of the water each time the battery dies. The next technology is using solar panels. An advantage is that it uses a renewable energy source. A disadvantage is that it charges batteries at a slower rate compared to charging the batteries manually using a charger and power outlet. Let's talk about the chosen technology to recharge our power supply, which is going to be solar panels. After comparing multiple solar panels on the market, we ended up choosing the semi-flexible monocrystalline. This model offered a power of 5 watts, while the others only offered 1 watt. Another factor is its weight. It has the lightest weight of the researched options, which is an important factor to consider when it comes to a floating device that remains on the water. The working temperature was also among the best of the options, meaning it can work in weathers that are both very hot and very cold.
In our project, the protection of the sensitive electronics components, particularly the PCB, is important to ensure reliable and durable operation. After careful consideration, we have chosen to utilize foam as a protective material for the PCB that will be carried inside the plastic box. The selection of the foam as a protective material for the PCB in our floating lab project offers numerous advantages, including shock absorption, moisture resistant, thermal insulation, customization capabilities, and cost efficiency. This choice ensures the integrity and reliability of our electronic components, contributing to the success and long-term operation of the floating lab in gathering essential data from aquatic environments. In our project, we have carefully selected the DS18B20 temperature sensor as an ideal choice for measuring water temperature. This slide highlights the key features and advantages of using this temperature sensor in our project. The temperature sensor is an excellent choice for our floating lab project, providing an accurate and reliable measurements of water temperature. It is compatibility with a wide range of devices, waterproof design, and the convenience of the one-wire protocol make it an ideal option for our application. With its exponential precision and cost efficiency, the temperature sensor plays a crucial role in enhancing our data collection capabilities and enabling comprehensive analysis in aquatic environments.
For the power supply comparison and selection, choosing the best power supply battery for our needs is crucial to get the desired outcome in our project. There are many types of batteries that we consider to use in the project, such as lithium ion, nickel metal hydride, and lead acid. We have chosen the power source based on the reliability of the battery and its performance in our project. Knowing that the boards typically operate at 5 volts, we needed to consider the voltage of the battery. Also, the capacity of the battery plays an important role in determining how long it can power our boards. Having a rechargeable battery for our project is essential because of its cost effectiveness in the long run. Since our project is aimed to be used in lakes and areas where the environment could be affected greatly, choosing a source of power that minimizes the amount of harm it does to the environment is necessary to consider. By considering all these factors, we chose the best option that meets requirements for the project requirements, safety consideration, and the budget.
When looking for pH sensors, we had three things in mind: reliability, price, and accuracy. This led to us finding two options: the gravity analog pH sensor and the AnyLeaf. We first had to make sure that both our sensors of choice would be compatible with an Arduino and a PCB, which they both are by using I2C protocol. When comparing the two options, they both could achieve the same range of pH, being 0 to 14, but the AnyLeaf had a better accuracy of 0.01 compared to the 0.2 of the gravity sensor. Another concern for the gravity sensor was that it could have up to a 2-minute delay while reading the pH, which is not advantageous because of the complexity of our project where we are reading multiple sensors, while the AnyLeaf can provide real-time pH readings. And lastly, the price, where the gravity sensor was $30 cheaper than the AnyLeaf. We ultimately decided to select the AnyLeaf, even though it was more expensive. This was because the reliability and data collection would have made it hard to implement with other sensors and the extreme difference in accuracy. As one of our design requirements is pH reading, we decided to put an emphasis on this aspect. An extremely important part of our project is sending data from the lab toolkit to our database, and we looked into 4 different ways of transmitting our sensor data. At first, we thought about using radio frequency to locally transmit our data, but since we wanted our project to be more flexible by location, we decided to stay away from radio frequency transmission to avoid having a transmitter and receiver. Next, we compared the difference in cellular, Zigbee, and Wi-Fi transmission, where they all could achieve the goal of sending our data. We decided to rule out the cellular option because of the drastic price difference between the SparkFun LTE and the ESP 826 and the Zigbee CC2530, where it is over 10 times as expensive, which left us with just 2. And in the end, we decided to select the ESP8266 Wi-Fi module over the Zigbee CC2540. This is because the Zigbee is designed for home automation and takes advantage of meshed networks, which is not exactly ideal for our project. Since our project is located in a pond, we prefer a larger signal distance, making using Wi-Fi with ESP826 the best choice.
Let's talk about the software and hardware integration of our project. We will discuss about how the NodeMCU using the ESP8266 Wi-Fi microchip was used after getting Dr. Leaway's approval, of course, how it was used with the PCB and the database to have both software and hardware working flawlessly together. Our project has the PCB connected to the sensors to take the readings. The PCB is connected with the NodeMCU using serial communication so that the NodeMCU can get the sensors readings as well after they are sent by the PCB. The NodeMCU is programmed to connect to either Wi-Fi or hotspot, which has to be 2.4 gigahertz. Then it will begin an HTTPS connection for security with our database using MongoDB. The NodeMCU will then send to the database all the sensor readings as a JSON object every 2 minutes. After the readings are sent to the database by the NodeMCU connected to Wi-Fi or hotspot, they will be available for viewing on our website since the website is also connected to the MongoDB database. On the screen, you can see the code that was used to program the NodeMCU. So it connects here to a hotspot or a Wi-Fi 2.4 gigahertz. Here it will attempt to connect to the Wi-Fi. If it doesn't, it's just going to continue printing the dot over here, an error. Over here, after it connected successfully, it will begin an HTTPS communication. We use HTTPS for security, of course. Then it'll take the JSON object and send it over, and it will repeat after 2 minutes.
Now let's talk about our software block diagram. As soon as our lab toolkit is turned on, it will start recording and sending our sensor data so it can be viewed on our website. We combine all the sensor inputs into one JSON object using key value pairs for each sensor reading. We then use an HTTPS post request to send our data by using the MongoDB API endpoint, which also allows us to add a timestamp. This allows us to write our pond data to our database. The second part of our software diagram is our web server, which integrates the data being collected from the pond. On the right, you can see how the user will interact with our web server, where they'll be prompted to make an account, which we also will store in the database. The web server allows the user direct connection to the data that is being collected, where the user takes advantage of the RESTful APIs that we have constructed. When comparing our software stack from our original design in Senior Design 1 to now, we decided to make a couple of changes. The biggest one was switching from Express.js and Node.js to Next.js, which combines them both in an easier to manage alternative for creating API endpoints. Next.js also integrates better with React and is better for server-side rendering, which is important for our project where we are updating sensors information constantly. Also, we decided to do this because it is the easier integration with GitHub for deployment and their service for sale, which makes the deployment a lot easier because all we need is a GitHub repository. Also, we switched from using Bootstrap to Tailwind because it is directly supported with Next.js for styling. And lastly, we decided to strictly use JavaScript because it was easier to develop this project in just one language. For our project, we had 3 separate entities that needed to be programmed. And to achieve this, we used a combination of Arduino IDE and C++, or Visual Studios and JavaScript. We had to take different approaches for these tasks because they were completely different and were challenging to implement and connect. For our application, we attempted on making our project future-proof, and this started with our database, where we are using MongoDB Atlas, which consists of one database with 3 collections, where one collection stores all the sensor data from our lab toolkit with a timestamp and a unique toolkit identifier, and the other collection stores user information consisting of email address, hash password, and an array which is used for adding lab toolkits to their account. And the last collection is used for tokens for the forgotten password feature of our project. Features of our website include that it can be accessed from anywhere in the world by using the link on screen. We also have sign up and login capabilities, where the user can also update their password and reset their password by sending an email to their account. Once the user has signed in, they can view the data in table form and query the results, or they can view it in chart form and have it displayed on the X and Y axis of their choice. Also, the user can add lab toolkits to their account.
The data connected in this project can be standardized in a data type that contains essential information to optimize the efficiency and speed in the industry. For example, data type as JSON object to be uploaded to the database that contains timestamp for year, month, day, hour, and minute. It also contains pH, temperature of water in Celsius, and air quality, which also contains temperature and humidity. Other parameters could be determined empirically while using the tools and also depending on what experts demand for their studies and research.
With the estimated project cost, we estimated at the beginning of the semester that this project might end up costing $785. Moving on to the cost and budget. Around the middle of the semester, we had spent around $600 for our parts. This amount is lower than the budget we set out to be, a maximum of $1,000. Unexpected expenses had to be considered, as they often happen because of something like a broken part. We estimated that with unexpected expenses, we would spend a total of $800, $200 more than the cost of what was spent at the middle of the semester, and that would still be under our predetermined limit of $1,000. We indeed ended up spending $200 extra because of 2 iterations of PCB design, which brought our final total cost to around $800.
For the work distribution, our group consists of 3 electrical engineers, as well as 2 computer engineers. The successful end result of the project was achieved because we were able to make the requirements we agreed on from the beginning. In order to utilize our skills in the most optimal way, the work distribution for our project is shown on the slide. The work distribution included 2 sides of the project, the electronic side and the software side. The roles in the project were chosen based on each student's specialization, interest, and strength in the project chosen.
In this semester, we have made significant progress towards achieving our goals. This slide outlined the key milestones we have accomplished throughout the project timeline. We have achieved significant milestones in our floating lab project, adhering to our projected timeline, from building and testing components to developing software, infrastructure, conducting through testing, and preparing the final report and presentation. Our progress reflects our dedication and commitment to delivering a successful project. With this milestone accomplished, we move closer to our ultimate goal of providing researchers with a comprehensive toolkit for data gathering and analytics in aquatic environments.
We're bringing you an amazing piece of innovation that flawlessly integrates software and hardware to have a floating device on the water. Our project reads 4 data points using carefully researched sensors and sends the data to a database, which is connected to a website for further studies. In the next section, our hardware team will present an overview of their beautifully designed system.
Now we are going to talk about the hardware system in our project. We designed our system so it can be used easily by the user. And one of the main things that's going to help us to do that is by using solar panels in here. This solar panel is going to convert the 6 volt captured from the solar panel, and it's going to be powered through the battery. The battery is going to be connected to the solar panel, which can convert the 6 volt into 5 volt into this solar power manager. The solar power manager is going to boost up the voltage and gonna put it into a 5 volt to power the PCB through the serial communication. Here we're gonna demonstrate the amount of voltage that is being captured from the solar panel. The solar panel is gonna capture a voltage of 4.2 and it's gonna be capturing the 3.7 voltage battery here. So it's gonna be charging the battery at the same time. For the board, the solar power manager board gonna power the PCB, the printed circuit board, through the serial communication, the cable, the USB cable through the PC, and gonna power the PCB through this USB cable. So now we're gonna talk about the PCB and how it's being implemented in our project. My teammate Omer are gonna talk about the specifications of the PCB.
Okay, so from this point, we have the USB connection coming from the solar panel and the battery, and this is going to be connected to the PCB through USB. We can see that this gets power from this USB connection. We can see the ADMega MCU, the crystal oscillator, the capacitors, and this configuration. This is a specialized pin socket that is connecting all the sensors that are managed by this project. The ESP MCU is also connected to the PCB. We can see a pH sensor, which is I2C. This communicates through I2C. We can see also the geek funk sensor. That's one wire communication, also connected to the PCB. And the air sensor, air quality sensor, that's connected to the same specialized pin socket that was designed in the PCB. We can see that this is the pH sensor, the water temperature sensor, everything connected, sealed. This is waterproofed. We can see this is waterproof with silicone, and at this side we can have the air quality sensor that's catching important information about the place where the boat is standing in that moment. This whole system is managed through this PCB, which is conformed by ATmega 328 microcontroller and the ESP.
Moving on to the software side of our senior design project. We started the development by using Next.js. Next.js is a React framework. React is a JavaScript library used to build web applications rendered in a client's browser with JavaScript. In other words, the whole website of our project was developed using Next.js. After development was completed and tested in localhost, which is a local server environment, it was deployed using Vercel. It was then tested again after deployment to make sure that everything runs correctly. Vercel helps deploy Next.js applications to the internet. The link to our website is displayed on the screen. Data regarding our project is stored using MongoDB. MongoDB is an open source NoSQL database management program. In our project, it stores users' credentials, pond data read from sensors, and temporary tokens generated when a user forgets their password, all in 3 different collections. Our website is connected with MongoDB to store the mentioned user credentials, retrieve data read from the sensors to display them on the main page, and more.
Hi, I will now show off the website part of our project. We have created a full stack web application to display the data collected from the pond, so the user can remotely monitor their body of water by going to this link above. First, I'm going to create an account. By pressing sign up, I type in my username and type in my email and give it a password. Right there. After creating an account, an email is sent to that user showing that the account has been created. I will now log in with the email provided and the password provided. Now, after signing in, I have access to all the data that my lab toolkit has been collecting. As you can see, the date, pH, air temperature, humidity, and water temperature all display in this table. Also, you can search, so I can search for a pH value greater than 7, and all the results with that show up. And since we're in Florida, I'll do air temperature greater than 100, and search, and all the ones like that show up. Also, if tables aren't your forte, we have a view charts part, where all the data is displayed in this beautiful chart, and you can change the axes and they update in real time. So you just want to see pH versus air temperature. You can see all the data points. It is responsive. You also might have noticed in the top right corner, we have this drop-down menu where the user can update a password, add a toolkit, or visit the About Us page or log out. First, I'm going to show the update password. So here, I can type in a new password, and I'll do a 12-digit password, and update it. And to show that it works, I'm going to log back out and sign back in. And as you can see, the new password is now updated. A feature that we've partially implemented is the Add Toolkit. So to add a toolkit, all you need is your email and number, and this will post to the database, adding this to your account. Right now, this has minimal functionality because we only have the one lab toolkit, so all the data is just displayed in this table here. But in the future, we are going to have it so you can select which toolkit you want to view. Also, we have an About Us page, which just talks a little bit about us. And the last feature I'm going to show you is the Forget Password. Let's just say I forgot my password and I want to reset my account. I'll press this button here, type in my email, press the button, and if an account exists, that email, a reset link will be sent to it. And here, a link has been presented to me, and I'm going to follow this link, and it takes me to this page where I can type in my email. I'll type in the secure token that is provided from the email right here. I'm going to copy and paste it, go back here, type in the secure token, and I'm going to give a new password. I'm going to go back to a 9-digit password. I'll do test1, and I'll reset my password. Now I can log back in with the new password, and I will have access to all my data again. Thank you for going through this walkthrough with me of our website, and I hope you visit our site. Thank you.
Today, I am thrilled to share the exciting results of our project's testing phase, where we have made significant strides in achieving our engineering specifications. The three engineering specifications I will be discussing are: the system shall measure the water pH and collect other data from sensors every 2 minutes. The system shall transmit the reading to the cloud every 2 minutes. And the system shall be moved with a remote controller with a response time less than 2 seconds. pH and data from other sensor reading. Using carefully selected sensors, our project collects reading regarding the water pH, water temperature, air temperature, and air humidity every 2 minutes. These readings are then transmitted through Wi-Fi to our database and made available for viewing on the website that is connected with that database. Transmitting data. In this video, you will witness our system in action, moving to different locations on the lake to collect a diverse range of data, which, with each move, we gather valuable insights into various environmental parameters, including water quality and more. These continuous data streams enable us to monitor and analyze the dynamic changes occurring in our natural environments. What makes our system truly exceptional in the refresh of rate cloud readings. Every 2 minutes, the cloud receives updated data, providing us with a near instantaneous understanding of the environmental conditions. This high refresh rate allows for prompt identification of potential changes or differences, enabling timely intervention and conservation efforts. The remote controller. The system shall be moved with a remote controller and the response time will be less than 2 seconds. The remote controlling functionality of our system has proven to be highly responsive, providing us with unparalleled precision and agility. With this exceptional control over navigation, we are able to explore water bodies with remarkable accuracy, allowing us to target specific areas of interest and collect data from diverse environments. The accomplishments we have achieved through fulfilling these engineering specifications speaks volumes about the potential of our project. We are on the brink of revolutionizing environmental monitoring, gaining a deeper understanding of our natural world, and making informed decisions to protect and preserve our precious ecosystems.
After extensive effort and countless hours of dedication, we have successfully developed a fully functional system that meets all of our expectations. We have overcome technical obstacles and challenging deadlines, since the summer semester is significantly shorter than fall or spring. We are delighted to announce the achievement of a fully functional prototype that integrates software, a cloud live database accessible via secure website utilizing user credentials, electronic circuitry that supports hardware and interfaces it with the software, as well as a floating platform that demonstrates exceptional mechanical versatility for project mobility on any point within a lake. All components have been carefully designed and organized in a cohesive manner. As a unified team, we proudly present the completed project by Engineering Group 07 at UCF. This project is presented to Dr. Lei Wei and our distinguished professional reviewers. Group 07 is conformed by the following members from left to right in the picture: Ross Springstead, Computer Engineering; Homero Rodriguez, Electrical Engineering; Mina Jones, Computer Engineering; Said Haddadin, Electrical Engineering; and Ali Ahmed Al-Kusavi, Electrical Engineering. Our goal is to produce a low-cost but effective tool that provides reliable and significant data in real time from the lakes. This data could be used to better understand lakes' health and to predict unwanted phenomena, for example, toxic algae blooms, hazardous bacteria colonies, mosquito larvae, and other insects, and also to analyze the biochemical composition of the lake.